Okay.
Thank you. Good morning. We had mentioned that a typical refractory microstructure consists of crystals, glass, and porosity. So we went over crystal structures. We talked about ionic and covalent bonding, and ions that have high charge, small size are going to result in strong bonding, which translates into high melting temperatures, which is important for refractories. And we looked at some of the different common crystal structures for some typical refractory materials. So crystals are one aspect of the microstructure, and so are glasses. So I put a lecture in here on glasses. If there's a small amount of glass present, it's usually at the grain boundaries. If there's a large amount of glass present, you can consider it a second phase. And if you have as much as 30% glass present, that's the point where you lose structural integrity at high temperatures. So any glass present tends to lower hot strength, it lowers creep resistance, and there's usually some amount of silicate glass present in refractories, especially in the alumina silica refractories and then some of the basic refractories, especially if there's a chrome type material present. So we'll go over the definition of glass, uh, definition of glass transition, and we'll look at some glass structure composition relationships. There's a random network theory, a bond strength theory. There's certain elements, uh, structural elements that are in these models, and then we'll look at chemical compositions, primarily silicate glasses, which are what is present in refractories. And then we'll look at viscosity, define viscosity, and look at how the composition of the glass affects the viscosity. A viscous glass at high temperatures is not as serious as a glass that's fluid, because that will really lower the high temperature performance of a refractory. So glasses have two characteristics. There's no long-range periodic arrangement of the atoms, and there's this time-dependent glass transformation region. So a glass is an amorphous solid. It's devoid of long-range periodic atomic structure, and it has to exhibit this glass transformation range. So this is a plot of enthalpy versus temperature. You can also plot volume versus temperature. It will be the same type of plot. So enthalpy, again, is internal energy plus work. And again, you can plot volume versus temperature. It's kind of easier to think of volume instead of enthalpy. So we'll look at what happens during crystallization. So it's this curve here. You have liquid, and then the crystal forms. So you start out with a liquid. You cool a liquid to its melting temperature, Tm. Tm is the melting temperature. And when the liquid crystallizes, you have an abrupt decrease in the enthalpy when crystallization occurs. So that's that large decrease. If it were volume, you'd also see a volume decrease. So now you have a long-range periodic atomic structure, and you have this discontinuous change when you crystallize the glass. And then further decreasing the temperature, you have this gradual decrease in enthalpy because the heat capacity gradually decreases. If this were volume, you have a contraction as you decrease the temperature. So that's what happens when the liquid crystallizes. And this is the case, what happens when it doesn't crystallize, so no crystallization. So you have a liquid, you reach its melting temperature, so it's supercooled below the melting temperature. It doesn't crystallize, so now you have a gradual decrease in enthalpy or volume with increasing viscosity as the temperature is lowered. So it's not discontinuous, it's a continuous structural rearrangement. Then you reach this point here where it deviates from linear behavior. So the atoms cannot rearrange to equilibrium in the liquid structure because the time allowed is not long enough because the viscosity is increasing. And then finally, you reach this point here where the viscosity is high and now the liquid structure is fixed. So there's no more atomic rearrangement at that point. And then after that temperature is reached, you just have a gradual decrease in the enthalpy as the heat capacity decreases with decreasing temperature. So here's your glass transformation range. So this is the temperature region lying between these limits where the enthalpy is that of the equilibrium liquid and that of the frozen solid. So those are the two endpoints for the glass transformation region. And that glass transformation region is a function of the cooling rates. So the glass transformation region shifts to lower temperatures as you go to lower cooling rates. So this top curve here is for fast cooling. Here's your transformation range. And then the bottom curve is for slower cooling. So the transformation range is shifting to a lower temperature. So the slower cooling rate allows the entropy or volume to follow the equilibrium curve to a lower temperature. And then there are two additional points to define here. These are for the fictive temperatures. So this defines the difference in thermal history between slow and fast cooling. And that defines the fictive temperature. So that's the temperature where the structure of the glass is the same as that of the equilibrium liquid. So if you extrapolate these curves, the glass and supercooled liquid lines, extrapolate these curves, you end up with that point there. That's the fictive temperature for fast cooling. If you extrapolate that curve and this curve, that's the fictive temperature for slow cooling. So the intersection of those lines defines the fictive temperature. So the slower the cooling rate, the lower the fictive temperature. And again, the fictive temperature is where the structure of the glass is the same as that for the equilibrium liquid. Below the fictive temperature, the glass structure is fixed. So that's what the glass, well, those are the definitions for a glass and how it behaves when it's cooled from a high temperature. So there are different theories for how glass forms. One is the random network theory. And in this theory, the glass lacks long-range periodic structure, but it allows for structure on a much smaller level. And these small structural units control the properties. So the random network theory, there was a person named Zachariasen. He developed a set of rules for glass formation and glass structures. So his rules give a continuous three-dimensional network with no long-range order. So I have the rules listed here for a simple oxide glass. So each oxygen atom is linked to no more than two cations. So this is that typical tetrahedron unit with four oxygens and silicon at the center. So the higher coordination numbers for oxygen prevents the variation in cation-oxygen-cation bond angles necessary to form a non-periodic network. So each oxygen atom can not be linked to no more than two cations. So the oxygen coordination number of the network cation is small. It's 3 in a triangular coordination or 4 in a tetrahedral coordination. Then these oxygen polyhedra, whether it's a triangular or tetrahedral, can only share corners. They don't share edges or faces. And at least 3 corners of each oxygen polyhedra must be shared in order to form a 3-dimensional network. So this type of sharing of corners locates cations as far apart as possible. So that's for a simple oxide glass. If the glass is more complex, if there's glass modifiers or glass intermediates, the glass must contain a high percentage of network cations that are surrounded by the oxygen tetrahedra or the oxygen triangles. Again, the tetrahedra or triangles only share corners. And now some of the oxygen atoms are linked to only 2 network cations and do not form bonds with any other cations. So that's where the non-bridging oxygens come from. So in this random network theory, the networks are distorted. There's no long-range periodicity. How is that accomplished? Well, there's variation in the bond lengths, variation in the bond angles, and then these small structural units, they're allowed to rotate. So that makes a distorted 3-dimensional structure. So A here is a crystalline material, B is a glass structure. So in A203, a hypothetical crystal, we have ordered AO3 triangles joined at the corners. So the solid circle could be an A atom, and the open circles are the anion, which could be oxygen. So they're triangular units. They're all joined at the corners of these triangular type units at the oxygens. Then the glass, and A203 glass, is disordered. So you still have these A03 triangles, but now they're not joined in any periodic arrangement. So that changes the bond angle. So you can see how random this structure is, the way the triangular units are joined. So there's different number of triangular units forming these different rings. So that's the random network theory and the rules for forming a glass. The other common theory is the bond strength criterion. And this is based on bond strength, and that's used to predict glass formation. Sun developed this single bond strength theory. Basically, he's saying that if you have very strong bonds, that prevents the reorganization of the melt structure into a crystalline structure as you cool that melt. So strong bonds prevent the reorganization. And a single bond strength is defined as the energy required to dissociate an oxide into its component atoms into the gaseous state, and that's divided by the coordination number. So he groups them as glass formers, which would be something like SiO2, that forms a glass by itself. Glass intermediates, which do not form a glass by themselves, but will form a glass if there's a glass former present. So an intermediate might be Al2O3. And then glass modifiers do not form glasses, they just modify the glass structure. So glass formers, glass intermediates, and glass modifiers based on their bond strength. So if the bond strength is greater than 80 kilocalories per mole, it's a glass former. So here's the formula MYOX. M is your cations. These are glass formers. O is the oxygen. So this is B2O3, SiO2, GeO2, P2O5, V2O5, and ZrO2. So they're all glass formers. They have valences as listed here. And then this is the dissociation energy in kilocalories per mole for each one of these oxides. This is the coordination number. And then you divide dissociation energy by the coordination number, you end up with a single bond strength in kilocalories per mole. So all of these are over 80. So all of these are defined as glass formers. And the intermediates, again, intermediates do not form a glass by themselves, but if they're in the presence of a glass former, they'll enter into the glass structure. So the single bond strength is now between 60 and 80 kilocalories per mole. So again, the formula MYOX, this is TiO2, ZNO, PbO, Al2O3, BeO, and CdO. So these are the valences on the cations. This is their dissociation energy and the coordination numbers. And you divide the dissociation energy by the coordination number and you get the single bond strength. So these are all between 60 and 80. So these are glass intermediates. And then the glass modifiers have a low bond strength, less than 60 kilocalories per mole. Again, the formula MYOX. This is Y2O3, MgO, LiO2, BaO, I'm sorry, L2O, BaO, CaO, ZRO, Na2O, and K2O. Their valences, their dissociation energies, you can see they're getting lower. The coordination numbers are pretty high. So when you divide the dissociation energy by the coordination number, you get pretty low numbers for the single bond strength. They're all less than 60. So those are our two theories for glass formation, but those theories have elements of structural, there's structural elements for these models. So I've listed the required elements, and we'll just mention these very briefly. The coordination number of all network cations has to be considered, the distribution of bond angles and structural unit rotations, how these network units are connected, how the network makes a three-dimensional structure, this intermediate range order. Some of the small structural units can order into larger units. Glass can have morphology. There can be two glass phases present. The field strength, the bond strength, the bonding are all important. The interstitial volumes or free volumes in a glass network, a glass will have a lower density than its corresponding crystal structure, so it's going to have some free volume. And the minor constituent impurities are going to affect the glass properties. So the coordination number of all network cations, we'll look at the coordination number of all high field strength cations. They're going to occupy sites in the network, and they're going to determine the coordination unit. So these are providing short range order. These are the basic building blocks or units in the network. So there is very short range order, but no long range order. So a silicon would be in four-fold coordination in this tetrahedron. A boron would be in three or four-fold coordination. If it's in three-fold coordination, it's going to form a triangle. If it's in four-fold coordination, it's going to form a tetrahedron. So silicon and boron are glass formers. Aluminum and germanium are glass intermediates, will form a glass in the presence of a glass former. They can be in four or six-fold coordination, either in a tetrahedron or an octahedron. So you have to consider the coordination number of the network cations. And then the bond angles and rotations. So there's a distribution of bond angles. These structural units have different rotations, and those are the basic building blocks and how they're connected, and they're forming a random structure. So how are these network units connected? So the connectivity of the network addresses the number and arrangement of these bridging and non-bridging bonds, which link the building blocks. So we'll go over bridging oxygens and non-bridging oxygens when we talk about the glass structures. So a non-bridging oxygen is an NBO, non-bridging oxygen, and a bridging oxygen is just BO for bridging oxygen. So how these are connected, the connectivity number defined as the average number of bridging bonds per network unit. So for the dimensionality of the network, it describes the spatial orientation. So 2 or 3 dimensional networks. It just depends on how the structural units are put together. And then the nature of any intermediate range order. So some of these building blocks can be connected to form slightly larger units. So the intermediate range order is determined by the dimensionality. So again, building blocks connected into slightly larger units with an additional amount of order. So they can form possible rings or chains, and these are the building blocks that extend over a short distance. So it's not long range order, but it is a little bit more order than just an individual building block or unit. Glass can have morphology. Two glass liquids can form. They can form phase separation. They can even have a small amount of crystallization. So when you have phase separation, you develop a morphology in the glass. And we talked about field strength and bond strength. So we need to consider the field strength of the network. So forming and network modifying cations, we have to consider the anion field strength as well as the cation field strength. And that has to do with the Sun's theory. And then the free volume in a glass, it has a more open structure than its crystalline component. Interstitial or free volume. When we look at the arrangement of the coordination units in space, they form interstitial or free volume. So there's an empty space in glass, and that has a big effect on the properties. It controls density, thermal expansion, diffusion. So glass has a lower density than a corresponding crystalline material, and those open spaces are important for determining glass properties. And then minor impurities, they're going to control certain glass properties. And when we look at the silicate glasses in a few minutes, we'll go over how the impurities affect the glass network and the properties. So since silicate glasses are the glasses that you usually see in a refractory material, again, they may be present in small amounts at grain boundaries. They may be isolated between grains, but if there's a larger amount present, it's really a second phase. So we'll look at silicate glasses, alkali silicate, alkali alkaline earth silicate, then alkali alkaline earth aluminosilicate. So these are the typical glass compositions that you would see in a refractory material, especially the fire clay, the aluminosilicate type refractories. So the silicate glass is simply SiO2. The basic building block is this tetrahedron, a silicon oxygen tetrahedron, the SiO4 unit. So we have the silicon atom located at the center of this tetrahedron. So that's the basic building block in a silicate glass. Each atom has a coordination number. Each oxygen atom has a coordination number of 4. Each oxygen atom is shared between 2 silicon atoms. So these individual tetrahedral units are linked at all four corners, and they form a three-dimensional network. So if it's pure SiO2, you basically have 100% bridging oxygen atoms. And the short range order is due to these tetrahedron units. So that's the short range order SiO4 units. And then how they're arranged creates the glass structure that does not have long range order. So this is a schematic diagram of the silicate glass. The black circles are the Si atoms. The open circles are the oxygen atoms. And here's a silicon atom surrounded by three oxygens. This is just a cut in one plane. So there'd be a fourth oxygen atom sitting above that silicon atom to form the tetrahedron. So they're sharing oxygen atoms at the corners. The structure is random. And you can see when they share, this is a ring here, sharing the corners of the oxygens, they create this open space. So you're forming these tetrahedral rings, maybe 5 to 10, and then you're creating these void spaces. So that's what the a pure SiO2 glass would look like. So how do you have disorder in the structure? Well, you have variability in Si bond angles connecting the adjacent tetrahedra. So that's a bond angle beta. So here's a bond angle beta. So here's a Si004 tetrahedron. Here's another one, Si, and there's 4 oxygens. So this beta is the bond angle between these two tetrahedrons. Oops, gotta go backwards here. So variability in the SI angle, that's beta. Rotation of adjacent tetrahedra around the point occupied by the oxygen atom, linking the tetrahedra. This is a torsional angle alpha 1. That's over here. So this tetrahedron can rotate to form a disordered structure. Going the wrong way. Then the rotation of the tetrahedra around the line connecting the linking oxygen atom with one of the silicon atoms. This is another torsional angle, alpha 2. So this is alpha 2, indicating that this cone-shaped rotation. So bond angles and rotation of the tetrahedra create a disordered structure. And again, this is your basic unit, Si, with 4 oxygens. So the long-range disorder is primarily due to variations in the bond angles and the torsional angles. Plus, there's also some variation in the bond lengths. So the bond lengths may also change. So that's how a disordered structure is created for a silicate glass. You're not really going to see a pure silicate glass in a refractory material. It's going to have impurities. So here's an alkali silicate glass. These are defined as follows: 0 to 36 mole percent Li2O, 0 to 58% mole percent Na2O, or 0 to 55 mole percent K2O. And these are all in an SiO2 glass. So these are 2-component glasses. The basic building block is still the silicon oxygen tetrahedron, the SiO4 unit, with the silicon atom located at the center of this tetrahedron. Now, when you add an alkali atom, it forms a non-bridging oxygen atom. So each non-bridging oxygen atom is associated with a nearby alkali atom and that maintains the charge balance. It has to be electrically neutral, an ionic bond. These alkali atoms are going to occupy the interstices, or these open spaces in the network. And alkali atoms are not glass formers. They're not intermediates, but they're network modifiers. They just modify the structure. They cannot form glasses by themselves. So here's what happens when you add lithium, sodium, or potassium to an SiO2 glass. Here's your basic SiO-Si bond. You have a bridging oxygen between two Si atoms, and you add M2O, which could be Li2O, Na2O, or K2O. And now you break that oxygen bond, and you have a SiO-M and another SiO-M. So this is negative oxygen. The charge is balanced by one of these +1 cations and another negative oxygen bonded by a plus cation. So each alkali atom creates a non-bridging oxygen. So one alkali atom actually creates two non-bridging oxygens because there are two cations, +1 cations. So you can see how this disrupts the structure. This will have an effect on properties like viscosity. This will be a less viscous glass, so a more fluid glass. And the more fluid the glass in a refractory, the less desirable it is. So this is a model of the actual glass structure. The black circles are silicon, the open circles are oxygen, and the crosshatched circles are sodium. Here's your tetrahedron. Again, the fourth oxygen would be above the silicon atom. So here's your basic structural unit. Here's one tetrahedron and a second tetrahedron bonded with a bridging oxygen. And then this is a non-bridging oxygen right here. It's not connected to another oxygen in a tetrahedron, but it is sitting next to a potassium ion, which balances the charge. So you can see how the addition of sodium, in this case, disrupts the three-dimensional structure. And again, this will have a big effect on viscosity, which is one of the important properties of a glass in a refractory. If you're going to have a glass present, you want to have a viscous glass. You don't want to have a fluid glass at high temperatures. And there are refractories like AZS that you deliberately put in a silicate glass, but you put in a very viscous silicate glass. So in the alkali silicate glasses, whether it's based on lithium, sodium, or potassium additions, you can calculate the concentration of bridging and non-bridging oxygens per silicon oxygen tetrahedron as a function of these alkali contents. So Q sub M is the concentration of bridging oxygen atoms per silicon oxygen tetrahedron. So N can only vary from 0 to 4. So if it's Q0, you have an isolated silicon oxygen tetrahedron with no bridging oxygen atoms. If it's Q sub 4, it's a fully linked silicon oxygen tetrahedron with 4 bridging oxygen atoms. So this would be for your pure SiO2 glass. And then if it's from 0 to 3, it's where you have created some non-bridging oxygens. So here is Q0, Q1, Q2, Q3, and Q4. And then the bridging oxygens per tetrahedron are given by this number. So if it's Q sub 4, there's 4 bridging oxygens. So that would be a pure SiO2 type glass. If it's 0, there's no bridging oxygens. And then you can have these other cases, Q3, Q2, and Q1 with 3, 2, and 1 bridging oxygens. So the bridging oxygens and the non-bridging oxygens have to add up to 4. So for Q sub 4, you have 4 bridging oxygens. You're going to have no non-bridging oxygens. And for Q0, you're going to have no bridging oxygens, but you're going to have 4 non-bridging oxygens. And then you can calculate the oxygen atoms per tetrahedron. In this case, Q sub 4, you have 4 bridging oxygens. So you're going to have 2 oxygens per tetrahedron. And then the other extreme, Q0, no bridging oxygens, 4 non-bridging oxygens. So you're going to have 4 oxygens per tetrahedron. And then these in between, Q3 is 2.5, Q2 is 3, and Q1 is 3.5. So you can also develop equations to calculate Q4, Q3, Q2, and Q1. So these are the compositional ranges in mole percent R2O3, whether it's Li2O, Na2O, or K2O, 0 to 33.3%, 33.3 to 50, 50 to 60, and 60 to 67.7%. So that would be the mole percent of R2O3 compounds. These are the equations, and then these are the fractional equations. So this is X between 0 and 33.3. You put in X here in mole percent, and you can calculate Q4 and Q3. This assumes that as you're creating non-bridging oxygens, they're going to go from Q4 to Q3. So no Q2 or Q1 arrangements are created. So when you add up to 33% R2O3 and you have all Q3 units, then you start creating Q2 units as you add more mole percent. And then the same thing, once you have all Q2 units, if you keep adding R2O3, you'll start adding Q1 units. So you just put in the values for X, you can calculate the amount of Q1, Q2, Q4, Q3, Q2, Q1, and Q0 units. And then this is the fraction of a Q3 unit, a Q2 unit, a Q1 unit, and a Q0 unit. So if you do those calculations and make the plot of fractions of tetrahedra versus mole percent alkali, it looks something like this. So here's Q4. This is 0% mole oxide. That would be 100% tetrahedra present. That would be pure SiO2. So here's Q4, and it decreases as you add mole percent alkali oxide. And then as that decreases, the Q3 content increases. So we assume the addition of each R2O unit creates only Q3 units until every tetrahedron in the network is linked to 3 bridging oxygens and 1 non-bridging oxygen. So now you have 100% Q3 units, 0% Q4 units, and then you start forming the Q2 units, and that'll reach 100% as the Q3 units decrease. Then you start forming the Q1 units, and the Q2 units decrease. And finally, you form the Q0 units as the Q1 units decrease. So this assumption, how you create only Q3 units until all the tetrahedron units in the network is linked to 3 bridging oxygen and 1 non-bridging oxygen. It's the same assumption for all of these as they create the different types of units. I don't know what that was, but then this is in theory, and in reality, if you measure this, it basically follows the theory. the lithium is the open triangles, the sodium is the open squares, and the potassium is the open circles. So you can see how these Q3 units form, the Q4 units decrease, the Q2 units increase as the Q1 units increase, the Q2 units decrease. So this actually follows the theory very well. Then you have alkaline earth silicates. So now you might have 10 to 20 mole percent Na2O, 5 to 15 mole percent CaO. And the Na2O can be replaced by K2O, Li2O, and the CO can be replaced by MgO, SRO, or BaO. So your basic building block is still the silicon oxygen tetrahedron with the silicon atom located at the center of the tetrahedron. So each alkali atom, we already discussed this, forms a non-bridging oxygen atom. And then each alkaline earth atom actually forms two non-bridging oxygen atoms. The alkali and the alkaline earth atoms occupy these voids or interstitials in the network. And there are both alkali and alkaline earth atoms are network modifiers. They are not glass formers or glass intermediates. So this is what this structure will look like. The open circle is oxygen, the small black circle is silicon. So here's your tetrahedron. We assume there's an oxygen above the silicon atom. The large black circle is sodium, and then the crosshatch circle is calcium. So you can see that a sodium ion forms a non-bridging oxygen, and it's Na2O. So here's both of the Na atoms forming two non-bridging oxygens. But then a calcium plus 2 ion forms two non-bridging oxygens. So here's one non-bridging, and here's another non-bridging. So one non-bridging oxygen atom per alkali ion, two non-bridging oxygen atoms per an alkaline earth atom. And then a little more complex glass, you have alkaline earth, and then you have an alumina addition. So this is an alkaline earth aluminosilicate glass. So you have RO, R2O, and Al2O3 in this silicate-based glass. Again, the building block is still the silicon oxygen tetrahedron with the silicon atom located at the center of the tetrahedron. That's the SiO2. Actually, this is SiO4 unit. So the aluminum oxygen tetrahedra substitutes into the network for a silicon oxygen tetrahedra. So this is the case if the concentration of the alkali and alkaline earth oxides exceeds that of alumina. So this would be for a small alumina content compared to the alkali and the alkaline earth oxides. So this is where alumina would be a glass intermediate. So the excess aluminum atoms are in octahedral coordination. 3 bridging oxygen atoms and 3 non-bridging oxygen atoms in each octahedron. So this is the second case. Now the concentration of alumina exceeds that of the alkali and the alkaline earth oxide. So higher alumina content, the excess aluminum atoms are now in octahedral coordination. 3 of those, there are going to be 3 bridging oxygen atoms and 3 non-bridging oxygen atoms in this octahedron. So the first case where the concentration of alumina exceeds that of the alkali and alkaline earth oxides, the excess aluminum atoms form these triclusters of aluminum oxygen and silicon oxygen tetrahedra with 3 coordinated oxygen atoms connecting the corners of the 3 tetrahedra. So the aluminum oxygen tetrahedra has an excess negative charge of -1. So an associated alkali atom, which is +1, maintains local charge neutrality. So there's one aluminum oxygen, a tetrahedron. You can also have an associated alkali earth atom, +2, maintaining charge neutrality. So that would require two aluminum oxygen tetrahedra. So this is the case where there's excess alkali or alkaline earth, and the aluminum atoms are now network intermediates. They're forming these aluminum oxygen tetrahedra. So the other case, each aluminum atom provides 1.5 oxygen atoms per aluminum oxygen tetrahedron. So the oxygen atoms provided by the alkali and the alkaline earth complete the required 2.0 oxygen atoms per tetrahedron, and then each aluminum atom removes one non-bridging atom. So actually, this is the first case where you have excess alkali and alkaline earth oxides. So what's happening, the alumina additions actually make a fully linked network. So as you're adding aluminum ions, you're creating more cross-linking. And finally, when the alkali and the alkaline earth oxides are the same concentration, you have a fully linked network again. So now when you have excess aluminum atoms and they're going to octahedral coordination, so there's more aluminum than the alkali and alkaline earth. So 3 bridging oxygen atoms and 3 non-bridging oxygen atoms create this octahedron. Again, concentration of alumina exceeds alkaline earth oxides. Now the aluminum ion is not a glass intermediate, it's a glass modifier. So these structures get quite complex. It's still questionable whether these structures exist or not, but this would be an Al+3 ion in an octahedral site. So here's 1, 2, 3 bridging oxygens, and then 1, 2, 3 non-bridging oxygens. And then another possibility when we have alumina exceeding the alkali and alkaline earth oxides in their concentration, you can form these triclusters of aluminum oxygen and silicon oxygen. So they're tetrahedra with 3 coordinated oxygen atoms connecting the corners of the tetrahedra. So here's an oxygen ion sharing a silicon, another silicon, and an aluminum. Here's an oxygen ion sharing silicon and 2 aluminums. And here's this tricluster in different orientation, but you have an Al+3, and then you have a bridging oxygen and 3 non-bridging oxygens. So which one of these structures are real or not? It's still questionable when glass scientists start looking at these structures. It could be any one of these structures plus this one or something else. But these are all postulated or possible structures. So the glass composition controls the viscosity along with the temperature. So viscosity is important for high temperature hot strength, for creep resistance, and for other properties like corrosion resistance and thermal shock resistance. So viscosity is simply a measure of the resistance of a liquid to shear deformation. So it's the ratio between the applied shearing force and the rate of flow of the liquid. So eta is the viscosity, and the units are poise or Pascal seconds. So poise would be P, and that's dynes second per square centimeters. A Pascal second is PA, short for Pascal, that's short for second. It's actually a Newton second per meter squared. It turns out that 1 Pascal second just equals 10 poise. So you have two parallel plates. F is the tangential force difference between the two parallel plates. A is the area of the parallel plates. D is the distance between the parallel plates or planes. And V is the relative velocity of the two parallel planes. So these are reference viscosities. These are points on the viscosity versus temperature curve. So this is your reference temperature. This is your viscosity, Pascal seconds. So the melting temperature, the viscosity is going to be between 1 to 10. The working point where you can form a glass into some useful object is about 10 to the 3. The Littleton softening point is 10 to the 6.6. The Littleton softening point is defined by an ASTM standard. It's based on a fiber elongation experiment. So you have a fiber, when it starts elongating at a certain rate, that corresponds to this viscosity, 10 to the 6.6. Dilatometric softening point, TD. That's when you measure a softening point in a dilatometer, and you actually have some load or stress on the sample. So this softening point, when you use a dilatometer, is going to be a little bit higher than the ASTM standard Littleton softening point. So 10 to the 8 to 10 to the 9. The glass transformation temperature is 10 to the 11.3. And then the annealing point is 10 to the 12, and the strain point is 10 to the 13.5. So the working range where you can actually form a glass is between the working point and the softening point. The annealing point, which is 10 to the 12, it's a pretty rigid material, but you can relieve the stress in 15 minutes, the stress when you cool it, that forms. And the strain point, 10 to the 13.5, it's still quite rigid, but you can relieve the stress in about 6 hours. So those are the different reference temperatures. And if you plot log viscosity versus temperature, you get a curve that looks like this. The viscosity is decreasing with temperature. This is your melting temperature. Here's your working point. Here's your softening point. Here's the glass transition by the dilatometer method, the glass transition by the fiber elongation or Littleton method, and finally your annealing and strain points. So viscosity is temperature dependent. It follows this Arrhenius equation. So eta, the viscosity of the liquid equals eta 0, which is the constant. Then it's E to the delta H eta divided by RT. Delta H eta is an activation energy for viscous flow. R is the gas constant and T is the temperature. So this is the Arrhenius equation. So if you increase the temperature, the exponent is getting smaller, and then the viscosity goes down, and you have a more fluid liquid. So increasing the temperature lowers the viscosity as an exponential relationship. So the composition effects are related to the structural connectivity. Anytime a compositional change reduces the connectivity, creates more non-bridging oxygens, you reduce the viscosity. And anytime the compositional change increases the connectivity, increases the bridging oxygens, that'll increase the viscosity. So for temperature effects, there's two ways to describe the viscosity. One is isothermal and one is isocom. So an isothermal viscosity, you're reporting viscosity at a specific temperature. In isocon viscosity, you're reporting a temperature at a specific viscosity. So it's just the reverse. So silicate is the most viscous of the common glass forming oxides. Is the highest viscosity. So this is a plot of the log of viscosity versus the inverse temperature. This is in poise, this is in 10,000 over temperature, but up at the top here is temperature in degrees C. So temperature increases from right to left. And then this is the viscosity curve. So as you increase the temperature, the viscosity decreases. The slope of these curves is given by this Arrhenius equation. If you do a log-log plot or log temperature plot, delta H eta is the slope, is the activation energy. In this case, it's 170 kilocalories per mole. And then it's common as you increase the temperature, the activation energy changes because the slope changes. So it's a little bit lower here at the higher temperature, 123 kilocalories per mole. So you do a log temperature plot, you can calculate the activation energies. So that's for a silicate glass. And in this whole temperature region, you have these SiO4 tetrahedrons. They're all tetrahedrally connected in the network. So they're all bridging oxygens, no non-bridging oxygens. So when you add an alkali, you have an alkali silicate glass. So small additions of alkali oxides really decrease the viscosity. So here's another log viscosity plot. This time we're plotting it against the mole percent R2O3 additions. And both of these plots are at 1700 degrees C. So if we put SiO2 on this plot at 1700 degrees C, its viscosity is 10 to the 7, and these are in Pascal seconds. So it would be up here somewhere, the viscosity of the silicate glass. So as you add K2O, the top curve, and Na2O, the bottom curve, you can see the drastic decrease in viscosity. So as you're adding Na2O or K2O, you're forming these non-bridging oxygen atoms. You're reducing the network connectivity, and you're really decreasing the viscosity. So if you have a silicate glass in a refractory and there's a lot of sodium and potassium present, it's going to be very fluid. So in these alkali silicate glasses, the alkali oxide type really has only a small effect on the viscosity. What has a big effect is the concentration of the oxide. So this is log viscosity against mole percent alkali additions. And there's different temperatures here, 1400, 1300, 1200, and 1100 degrees C. So K2O additions are the solid triangles, LiO2 are the solid circles, and then the solid triangles are Na2O. So no matter what temperature it is, you can see the viscosity decreases with increasing alkali content. And then as you increase the temperature, you're going in this downward direction. The viscosity is decreasing also. So whether it's K2O, Li2O, or Na2O, you see they're all falling on these curves. So the type of alkali doesn't really affect the viscosity as much as the concentration of the alkali. There's something known as the mixed alkali effect. So if you have a mixture of two or more alkali oxides, that lowers the viscosity more than the same concentration of a single alkali oxide. So temperature versus mole percent Na2O is X. So if X is 20, you're at 20 mole percent Na2O. If X is 0, you're at 20% K2O. So there's a minimum in each one of these curves somewhere towards the middle of this diagram. So these are the log viscosities. This is 8 poise, 10, 12, and 16. So the higher temperature has a lower viscosity, and the endpoints, whether it's 100% K2O or 100% Na2O, the combination somewhere in the middle reaches a minimum, and that's the mixed alkali effect. And then the alkaline earth silicates, they can exhibit a greater viscosity than the alkali oxide silicates at the same concentration. So and equal non-bridging oxygen atom concentrations. So the greater field strength of these divalent alkaline earth ions, alkali earth atoms like Ca plus 2, they have a greater field strength compared to the monovalent single charge alkali atoms. That tends to strengthen the glass network. So this is the change in viscosity with composition. This is the weight percent oxide. So if we just look at NGO and CaO, they're replacing Na2O, and you're actually having an increase in viscosity because of the greater charge on the alkaline earth ions compared to the alkali ions. And I think this is the last slide. The replacement of alkali or alkaline earth atoms by alumina reduces the concentration of non-bridging oxygen atoms and increases the network conductivity. So for the previous cases of MgO and CaO, the +2 charges increase the bond strength and increase the viscosity. But now the addition of Al2O3 replacing Na2O is making it's making the non-bridging oxygen atom concentration decrease, creating more bridging oxygen. So it's going to see an increase in viscosity. I think that is the last slide. So I tried to show you silicate glasses, alkali silicate glasses, alkali alkaline earth silicate, and then alkali alkaline earth alumina silicate glasses, and how the different concentrations of the impurities affect the viscosity, and based on how you create bridging and non-bridging oxygens. This is actually pretty complex, how these structural arrangements affect the glass properties and the viscosity. So that's what I have on glasses. And again, silicate glasses are common in all refractories, and some of them may have pretty high concentration of silicate glasses, especially in the low alumina fire clay bricks. So that finishes up glasses. We have 3 more lectures on phase diagrams. Phase diagrams are real important. The phase diagrams tell you the useful temperatures for refractories as a function of composition. So we'll go over the phase diagrams, and then we'll start on glass compositions. So have a good rest of your day, and I'll see you on Wednesday. Thanks again for attending.
Thank you so much.